Hi, and welcome to NVIDIA's Virtual Connect with Experts webinar. This is our monthly webinar series where you can learn from and ask questions directly to our CUDA experts on a wide range of topics. This month, we're very excited to present the CUDA-Q team, who will discuss their qubit-agnostic platform and programming model for hybrid quantum classical application development. We're going to kick off with a presentation from our experts and then open it up for questions. You can ask your questions by typing them in the comments section of your webinar platform. We may not get to all of them, but we will do our best. As a gentle reminder, by being here, you're agreeing to abide by NVIDIA's code of conduct. Please be kind and respectful to each other and to our panelists. With that, we're going to start off with introductions. My name is Katrina Reel. I'm a Principal Technical Product Manager on the running the CUDA education program at NVIDIA, and I'll be acting as one of the moderators throughout the event. And now I'm going to pass it over to Jin Sung, who will kick off introductions for our panel.
Hi, everyone. So my name is Jin Sung Kim. I'm from the quantum computing team at NVIDIA. I'm a developer relations manager. I'm joined with several of my colleagues here. Let's just go around in a circle, and I'll hand it off to my colleagues to introduce themselves. Monica, would you like to say a few words about yourself?
Sure. I'm Monica Van Dier, and I'm a senior technical marketing engineer in the quantum group at NVIDIA, and I lead the CUDA Quantum Academic Initiative. Pass it on to Mark.
Everyone, my name is Mark Wolf. I'm also a technical marketing engineer on the quantum team, working on CUDA-Q Academic and some of the other initiatives we have. Pooja, do you want to go next?
Hi, everybody. I'm Pooja Rao. I'm a quantum algorithm engineer at NVIDIA. I work at the intersection of quantum computing and high-performance computing. More recently, I've been working on using AI techniques for quantum computing. Really looking forward to this webinar. And Mike, if you want to go ahead.
Hi, everyone. I'm Mike O'Keefe. I'm a senior solutions architect on the higher ed and research team. We help researchers reduce time to results through accelerated computing solutions, and quantum computing is one of the areas I focus on. Jin, back to you.
Did we get Efrat?
Oh, sorry.
Hi, everyone. My name is Efrat Shabtai, and I'm a senior product manager at NVIDIA. I'm the product manager for CUDA-Q that we'll talk about today. So really looking forward to your questions in this presentation. Back to you, Jin Sung.
Great, thanks. So I'll show a couple of slides on our overall platform. Zach, would you mind pulling up my slides? Thank you. Yeah, so let me go ahead and tell you about some of the work that we've been doing in the quantum space and really the work that we've been doing with the entire quantum ecosystem. So first of all, we're not building our own quantum processor. There's plenty of people out there who are very, very good at that already. But what we are very good at and have a lot of experience in is building heterogeneous compute systems with new types of accelerators, networking them together, scaling them out, and making them into useful scientific tools. So what we think this will look like in the future will be a quantum computer of various modalities next to a supercomputer. So quantum computers are not going to do everything themselves, but will be a critical part of solving important problems that we can't solve today. And on the flip side, GPU supercomputers are very useful tools for making advancements in quantum computing today. And we think will be an important part of useful workloads with a quantum computer in the future. So what we have to do is carefully consider a fully integrated system, both from the low-level systems integrations to the high-level methods for developing applications. So this vision is our North Star. We call it the accelerated quantum supercomputer. This is what we're trying to help the entire ecosystem build towards. So what this is connecting QPUs of all architectures to AI supercomputers for the purposes of developing hybrid applications, leveraging AI methods for quantum, developing the low-level and low-latency connections between a QPU and a GPU, and all the way up to the high-level libraries for enabling the end user to program the system as they would a normal computer. So as a platform company, our success is dictated by the success of our partners. So when our partners succeed, we succeed. So we're really happy and proud to be able to partner across the entire quantum ecosystem. We have a pretty amazing ability and privilege to be able to work with nearly every quantum computing company, from early stage startups to some of the largest companies in the world. So how do we get to where we are today to where we want to be in the future? To really realize this vision of the accelerated quantum supercomputer, very broadly, the three biggest challenges are to build better performing quantum hardware, better algorithms and applications to identify useful workloads, and to be able to scale out quantum error correction. So we're building out a platform that we think is going to help with each one of these things. So CUDA-Q is our software platform and programming model for quantum computing. It's open source and qubit agnostic. If you're familiar with CUDA, it's the framework that has allowed the massive scale of the GPU and is the best way to program a GPU. So in a similar way, CUDA-Q is our framework for programming a quantum processor, integrating them into supercomputing scale GPU systems, and ultimately making quantum successful overall. And so a big part of this is the enablement and integration with the entire ecosystem. So the logos you see here on the right are QPUs that you can access today with CUDA-Q, with several more not listed here that are in the process of integrating. You'll notice that nearly every modality, qubit modality here, represented here, as well as both digital and analog quantum processors. Also highlighted here is our integration with AWS Bracket, which now hosts CUDA-Q natively on their environment. So you can access all the QPUs available there through CUDA-Q, as well as various GPU instances for high performance simulation. In addition to quantum hardware, we've also developed state-of-the-art tools for simulation. So for simulation, we've developed a set of libraries called cuQuantum, which are extremely performant and powerful tools for developing algorithms and applications and understanding scaling behavior. For us and our partners, simulation is a really complementary tool for quantum computing. So there's many reasons to leverage simulators. Many of our partners and users like to use them to prototype algorithms or workflows before they run them on real quantum hardware. Others like to use it to controllably study the effects of noise on an algorithm and error mitigation techniques. And even others help them use simulators to help them design and develop better control techniques or refine their parameter space for developing quantum hardware. So one thing that's important to mention here is that we release our simulation acceleration libraries independently from CUDA-Q so that every other framework within the quantum ecosystem can also pick up our acceleration capabilities. Now, on the opposite ends of the stack, we have a new set of libraries called CUDA-QX. These are high-level libraries for accelerating applications development. For CUDA, libraries have been a big part of making it easy to program applications on the GPU. So the first two we've released are CUDA-Q QEC for enabling quantum error correction and studies and workflows, and CUDA-Q solvers, which has built-in primitives for developing quantum chemistry applications. At the very bottom of the stack, we have a system and reference architecture called DGX Quantum. This is a system we developed in collaboration with Quantum Machines, which enables a very low latency connection between a GPU system and a quantum control system. So this is the first system of its kind. It won't be the last, where we have a direct coupling from a GPU to QPU and can start exploring workflows leveraging GPUs for things like real-time calibration, control, and to start to do investigations in real-time error correction. So this is our platform. It's open source and available to use. We build the whole platform, but we distribute it in a disaggregated ways. So our partners and our users can either take the whole stack if it's useful to them, or they can pick and choose what parts of it are most useful to them. So we're also, I want to mention that this model of the accelerated quantum supercomputer is already starting to happen at various sites around the world. The ones here are already deploying quantum processors next to GPU supercomputers and really starting to push the forefront of what's possible with GPU supercomputing alongside quantum computing. So with that, let me pass it to Monica to do a couple of examples.
Yeah, thanks, Jin-Sung. Zach, if you wouldn't mind sharing my screen. So that was a great overview of accelerated quantum supercomputing and the CUDA-Q stack. And so I want to dive into a little bit of a live demonstration to bring CUDA-Q to life and give you the basics on how to get started programming with CUDA-Q. So I know the audience is going to be coming from a wide variety of backgrounds. So I really do want to start, for those who've never seen the notion of a qubit before and are just here because they're interested in quantum computing, one way to follow along is to think about a qubit as a vector pointed in some direction on a three-dimensional sphere like depicted here. And qubits in different states are just going to point in different directions around that sphere. And we can change from one state to another by rotating that sphere. So the first example program that I'm going to show you is a very basic like hello world type of program for 1 qubit, but it covers a lot of the syntax that you'll need to get started with CUDA-Q. And our program is going to take a qubit in the state 0, which is pointing up here, and we're just going to rotate the sphere 180 degrees around the x-axis and bit flip it. So change a 0 state to a 1 state. That's the program that we're going to start with. If you're new to quantum computing, you might think, what is a quantum program? We can sort of think about a quantum program as having 3 components. The first is to initialize the qubits, and each row here represents a different qubit. So this would be a picture of a 3-qubit program. Then we need to manipulate those qubits. They're kind of storing information, and we're manipulating that information with gates that perform operations either on 1 qubit, like a rotation of that sphere that we just saw, or to entangle a couple of qubits with gates that operate on multiple qubits. And then the final state of the quantum program is to, or the final step of the quantum program is to measure the qubits to extract some information out of those when we execute that program. So let's just walk through the basics of how you program in CUDA-Q. It is a C++ or a Python language option for you to program. I'll just demonstrate this one here in Python. And so a quantum program can be thought of as, at the most basic level, as a function that we are decorating with the @CUDAQ.kernel. So you write a function just as you would in Python. We're defining a bit flip function. We want this program, like I said, it's going to be 1 qubit that we're going to flip from 0 to 1. So the first thing we have to do is initialize that qubit with the CUDA-Q vector. And this argument of 1 indicates that we're just going to have 1 qubit in our program. You could change that to 2 or 3 or 100 if you wanted. And then the next step is to manipulate it. But I'm just going to do this step by step to make sure that we have because my typing skills are, there we go. We first want to import the CUDA-Q library, right? It's already done, but I wanted to make that call out that was implicit in this notebook. So we've defined this function. And so let's just see if we've actually defined a function that does initialize a qubit in the 0 state. So I'll just go ahead and use the add to block sphere and the get state functionality of CUDA-Q to graph that qubit. And we do see that we have defined a qubit in the 0 state. And so now we want to flip it. So after we've initialized the qubit, we're going to apply an X gate. The X gate just rotates that qubit along the block sphere 180 degrees. So I've fixed my function there to do the bit flip. And then we can go ahead and graph the results of that qubit. And we see that we have changed the state of the qubit from 0 to 1. That's kind of like the most basic type of program that you'd write. And if you think about doing this with multiple qubits, you're not going to be visualizing all the qubits individually. And in fact, when you deal with entanglement, this notion of the block sphere sort of breaks down. So what we do instead is when we're writing a program for a quantum algorithm, we are going to do a couple of things. The first thing is that we are going to have to define how we're going to run that quantum program. And we do that with the set target command. And there are several different targets we can choose. We can choose a CPU, GPUs, multiple different quantum processors that we might have available. And the nice thing about that is once you've got your quantum algorithm written up, you can execute it on all these devices by just changing that target. So here we would be running it on a CPU if we use the QPP minus CPU. If I wanted to change it to a GPU, I would just change it to NVIDIA. So we want to define a function. This one will define a quantum circuit that does a little bit more. We'll have a quantum circuit on 2 qubits. So just like functions in Python, they can take arguments. The only difference is that our quantum functions here, our quantum kernels, have to take our arguments and have them the type be explicitly given. So here we're inputting the qubit count to say that we want to define a kernel with a certain number of qubits. We initialize those qubits with the Q vector, just like we did earlier in the previous example. And we apply some gates to those qubits. This being based in Python, we can use functionality from Python, like the for loops here, to simplify things down. So we can apply the gates. And then we take a measurement as a final step. Implicitly, if we don't specify it, the measurement's going to be done in the Z basis. Otherwise, we can specify different types of basises. Once we define that kernel, we can then draw the circuit diagram out. So you can see here that we have a 2-qubit circuit, and we are applying a Hadamard gate to put the first qubit in superposition, and then the control knot to entangle the 2 qubits. And as the final step, we are going to sample the kernel, which the kernel takes as input the qubit count, and we're going to sample it 1,000 times. So we're going to execute that kernel 1,000 times, and within those 1,000 shots, we see roughly 50% of the time we read out the 0, 0 state, and 50% of the time the qubits Q0 and Q1 are read out in the 1, 1 state. So sampling is one of the ways that we can execute quantum circuits. Another common way of executing quantum circuits is with the observe command. And what that does is it computes the expectation value of a Hamiltonian. So we can define our Hamiltonian using the CUDA-Q spin operators. In this example here, we just have the Z, Y, and X spins there applied to the 0 or the first qubit, respectively. And we're going to observe the expectation value of our kernel applied to the qubits with that Hamiltonian, and extract out the expectation value. And so in this case here, we get 0. And then the final way that you can execute the kernel is with the get state command, which will extract the probability amplitudes of the final state of the qubit. As we saw in this previous qubits, in this previous sampling, we saw 50% of the time we read out 0, 0, and 50% of the time we read out 1, 1. So the coefficients in the bracket notation of this quantum state would be 1 over the square root of 2 and 1 over the square root of 2, or 1 over the square root of 50%, 1 over the square root of 50. Or I'm sorry, the square root of 50%, the square root of 50%, which we see as the coefficients here, 0.707 and 0.707, when we just extract those probability amplitudes out. So just depending on what you're trying to do and what in your program, you may use one of these 3 execution models. And in addition to being able to input the number of qubits into the function or the kernel, you can also create parameterized kernels or parameterized circuits by adding an argument for parameters there, float values of theta, and run your sampling or expectation value computations similarly. So that's a really quick run through of the basics of CUDA-Q syntax. And I think now this is the end of our presentation that we had planned, and we're opening it up to Q&A at this point. So hopefully you got a little bit out of this. Think about what we've learned. If there's something you're curious to learn more about, or even how to get started, just let us know, and we can answer those questions now.
And just encouraging you all, please don't be shy. We're more than happy to go through anything that's on your mind. So even if there's just a topic that you'd like to learn more about, feel free to put it in the comments. Thank you. All right, so our first one, exciting topic. Curious how CUDA-Q is bridging the gap between classical and quantum workflows. And we did go through some real world demos, but of course we could always talk about more case studies and real world demos as well. But just throwing that over to the team.
Yeah, so I think one very obvious use of using classical and quantum workflows is actually quantum error correction. So this is the process of detecting and correcting errors as they occur in real time, and is kind of one of the key things to unlock useful quantum computing in the future. So the process of actually detecting and figuring out what is the real error that occurred on the quantum processor is a classical process and needs some real-time compute, and is actually a non-trivial classical compute question. So that is actually one very concrete workflow that will require the tight integration of classical and quantum workflows. That's something that we're building towards. But there's also applications where much of the computation actually will want to happen on a classical supercomputer, and then portions of it will be passed to a quantum computer. So one example of this is recent work that we had with AstraZeneca, IonQ, and AWS. And this is a process where we were simulating a molecular kind of quantum chemistry problem, where parts of the problem were run on the quantum processor, and then the results of that were fed to a pretty massive GPU cluster for post-processing. So this is something like 40,000 GPU hours used to post-process those results. So another example of kind of a quantum chemistry workflow that really is is required to use a large amount of GPU compute alongside a quantum processor.
All right. How do we know the qubit is in both 0 and 1? The superposition. I'm assuming that this is I'm just going to throw this out and see what you have to say about superpositions.
I can take a stab at this, and then if anyone else wants to add their own color to it. So basically, in an experiment, you're measuring the qubit, and you have to measure it in a certain so-called measurement basis. And so when a qubit is in the superposition, you'll measure a probability distribution where the qubit is in either the 1 state 50% of the time and the 0 state 50% of the time. But there's other measurements that you can do. For example, if you rotate it back into one of these basis states, you'll get the qubit in either the 0 or the 1 with 100% of the probability. So what that means is if you rotate it back into the basis state from the superposition state, you kind of understand that the qubit was truly in the superposition state before from the probability distribution.
Yeah, and I go, Zach, if you could pull up my screen again, I can just show an example of that a most basic superposition. And if you want to learn more about this topic too, we have some notebooks on CUDA-Q Academic called The Quick Start to Quantum. And the first notebook actually walks through more details of exactly what Jin-Sung mentioned with the different basis measurements. But this is an example here. I've just taken our previous code and edited it a little bit, where we have 1 qubit, and we are applying the Hadamard gate, and the Hadamard gate will take a state that was originally in the 0 state, which is how all of the qubits are initialized in CUDA-Q, and transforms it into a state of equal superposition or along the x-axis of that black sphere. And when we run and execute that program, we see that 50% of the time when we do a measurement, we get a 0, and about 50% of the time we get a 1. So that's qubit, but prior to the measurement, was in a state of superposition between 0 and 1.
All right, great. Let's our next question. How can we apply quantum computing to real-world computing scenarios such as browsing the web?
Yeah, I can take that. Maybe I can show the CUDA-Q application hub. So let me share my screen real quick. Zach, if you can pull that. So this is part of our documentation. You can see that in the application folder. Basically, this is all of our real-life applications developed using CUDA-Q, many times with our partners or some joint projects or implementing some academic paper. And this will give you some really great examples, real-life examples of how you can use CUDA-Q and how you can use quantum computing. You can filter by specific domain that you're interested in, or by specific backends, whether it runs on a simulator, on specific QPUs, which type of QPU modalities, and so on. So this is a great resource, and we'll also put this link in the chat.
I'll also add to that. Another good place to look is the NVIDIA tech blog. You can search for the tag quantum computing, and there's a number of stories that both intersect with these applications as well, and kind of walk through real world scenarios where we've worked on different use cases with partners, and they've used CUDA-Q to do a number of different things, from chemistry simulations to finance applications and things like that. So some of those have more of the real world applications, and then there's often a complementary notebook in the applications section.
Thank you so much. And we can.
I have one more thing to say to that.
Oh, of course, absolutely.
There are going to be some problems in which quantum computers are going to be used to come up with better solutions or more efficient solutions. And then there are problems that quantum computers are just not going to be useful for. Like, you're not going to use a quantum computer to check your email. So that's just something I think that was implicit into that question about browsing the web. But that's something regular computers you just fine with.
Great. Okay, next one. Let's see. How scalable is CUDA-Q currently? What is the max number of qubits that have been simulated to date at NVIDIA?
Yeah, so this is a bit of a tricky question because there's a bunch of different kind of advanced simulation techniques that people can leverage for different applications. So kind of the most brute force way of simulating qubits is using something called a state vector simulator. So this is when you hold all of the quantum information in the memory of a classical computer. And so this scales kind of exponentially in memory with the number of qubits. So every time you add another qubit to the mix, you have to double your memory requirements. So kind of the upper limits on that are probably in the high 40s or low 50s number of qubits. That being said, there are a number of different advanced simulation techniques. So for example, leveraging tensor networks or polypath propagation or kind of Clifford simulators that can also simulate much larger numbers of qubits for specific applications. And we should also note that for simulating kind of realistic quantum systems today, the quantum hardware has noise, and the effect of noise is to essentially remove information from the system. So it's actually a bit easier to simulate realistic noisy quantum hardware using kind of advanced simulation techniques. So with tensor network methods, people have leveraged GPUs to simulate on the order, I think the highest number I've seen is something on the order of 40,000 qubits using a tensor network method. And then there's other methods like Clifford simulators where for specific quantum applications, these are actually extremely efficiently simulatable. So of the order hundreds of thousands or millions of qubits for specific applications.
Yeah, and maybe one thing I'll add is one of the design features of CUDA-Q is to make it easy to switch out the backends. So if you're trying to simulate some number of qubits, you can experiment with density matrix versus state vector versus tensor network simulation, and also expand that to multiple GPUs as you start to scale out.
And just to add to what Mike said, we make it very easy in CUDA Quantum to switch from different backends. So it's typically just a single line of code. We assume zero knowledge of CUDA or MPI or any of these programming models in that. And we make it really easy for application developers to experiment between these different backends and to be able to use multi-GPU backends fairly easily.
All right, we'll move on to the next one. How scalable is CUDA? Oh, we've already done that one. I'm so sorry. Any use cases for using quantum In a real workflow. Oh, we already went through this one as well, brought up a bunch of examples there. So for sure, take a look at what's up there. Okay, and then can CUDA-Q enable real-time AI-driven optimization of quantum algorithms?
That's a great question. We actually have some active work on this space. Maybe Pooja, you want to say a few words about that?
Sure. So we actually really focus on leveraging AI to enable and enhance quantum computing and what quantum computers can do. So I'm going to interpret this question more broadly as how can we leverage AI to progress quantum computing, and how can, there is a very harmonic relationship between quantum computing and AI. In the future, we can see them like working really closely together. So there's a number of ways in which we support that. So you can actually design QPUs or quantum hardware using AI techniques. But that's more like use of AI for advancing quantum computing. But there are several other algorithms. One of those algorithms is generative quantum eigensolver that we collaborated with Toronto. And essentially what we do there is we use scalable AI techniques such as generative models to generate efficient quantum circuits and then run them on quantum computers to solve problems in optimization and quantum chemistry and so on. We have several other algorithms such as QAOA, GPT, and all of those algorithms and applications you can find in the application page that Efrat and Monica shared earlier. I highly recommend checking them out. But essentially, there are certain things which today's quantum computers are not very good at, or they are very noisy at, or are not scalable. So we can leverage those AI techniques to get around some of those limitations of quantum computers and build scalable applications. So if you're interested in specifics, I highly recommend checking out our applications page. And 3 things that I've listed here is QAOA GPT algorithm, which is used for quantum chemistry. The second one is the generative quantum eigensolver, which has a lot of application in itself, and we have applications based on that as well. And the third one is what I've listed is using AI for quantum computing techniques, for quantum computing hardware optimization.
So there are also some examples of folks out in the ecosystem leveraging our DGX quantum system. So this is our system that tightly couples a GPU to the quantum control system of an actual quantum processor, and are actually leveraging things like reinforcement learning to automatically calibrate the quantum processor. So on the calibration side, there are indeed many applications as well.
And of course, quantum error correction. The decoders and quantum error corrections use AI pretty heavily.
All right. How would you suggest current students get into quantum computing, given there aren't many programs yet with it being so new?
That's a great question. We do have the CUDA-Q academic tutorial notebooks that are on GitHub. They're openly available and free for you to use. And almost 90% of those notebooks can be run on your CPU. So, if you're really motivated, you can install CUDA-Q on your laptop. If you're not so motivated to do that, you can also run these notebooks on several of the online platforms like Colab or QBraid, and experiment with basic quantum algorithms and get your feet wet into quantum computing there. One of the great things about CUDA-Q is that we are qubit agnostic. So when you're learning the programming language, you know that you can run it on any type of quantum hardware that eventually might come into the industry later on. And also we do have this ability to write a workflow that's hybrid in nature, and the future of quantum computing is going to be hybrid. So learning how to take classical code and mix it with the quantum code where it needs to be done, and how to do that is what the CUDA-Q academic notebooks are geared towards. They also cover things like scaling up quantum computation and dealing with some of the issues of the realities of quantum computation, like noise and error correction. So I would recommend hitting up that GitHub.
This is actually a follow-up to what you just answered. Is it possible to run this without a GPU or on Colab?
Yeah, so CUDA-Q will run on a, most of the functions will run on a classical computer. Of course, you're going to be limited by the number of qubits and the depths of the circuits that you can handle if you're running it just like on a CPU. And if you have a GPU available, even like the, the free instances that you might find online for limited time, that can handle some of the basic ones for learning. Of course, for doing experimentation and research, that's where the CUDA-Q shines with the GPUs, and it would be necessary. But for learning, you can start today on your laptop.
All right. As CUDA-Q evolves, how do you see it addressing the orchestration challenges between noisy intermediate scale quantum NISQ hardware and classical HPC resources at scale, especially for hybrid workflows?
So CUDA-Q is really built from the ground up to support hybrid workflows. So from a programming model standpoint, being able to very cleanly delineate quantum workflows and kernels that are intended to be run on a quantum resource. So both from the programming model perspective and from the systems perspective, it's really been built to address this challenge of bridging the gap between quantum and classical hardware.
Another example of that is joint work we did with HPE in terms of scaling, right? If you have a really large quantum circuit you want to run, but your quantum hardware is limited in the number of qubits, you need to break that circuit up into smaller parts and run those smaller parts on the smaller quantum hardware, and then stitch those results back together. And so we have a, oh, now the name escapes me. We have an algorithm that with the HP, maybe Jensen, can you remember the
adaptive circuit knitting?
Yeah, adaptive circuit knitting. Thank you. that carries that out. And CUDA-Q helps to orchestrate that, because what you do is you're taking that big circuit and you're breaking it down to smaller pieces. Some of those pieces could be run on a CPU. Some of them could be run on GPUs. Some of them could be run on a quantum processor or different quantum processors, all in parallel. And CUDA-Q is built so that you can orchestrate that entire workflow.
Right. And just to add to that, we actually have a backend that addresses this sort of like distributed model of computing. It's called the MQPU backend that parallelizes a lot of things. For example, if you have circuits that you want to execute in parallel, or for example, if you have a Hamiltonian with a really, really large number of terms, you can parallelize all those instances. And in the future, maybe the quantum computers will be, you can do such a parallelization with the help of quantum computers, but of course, that setup is not available right now. But CUDA-Q lets you experiment with that kind of distributed model of quantum computing using the MQPU backend. So if you're interested, please check that out. And we, again, have some really great examples on the documentation utilizing that backend.
Great. Does CUDA-Q support persistent GPU memory structures across conversational turns, especially when adapting quantum routines to real-time data streams and emotional voice inputs from systems like AI? This might be too specific to this particular area. Any comments on this one? Okay, we're going to move on to the next one. Let's see. Your quantum roadmap emphasizes massive computational throughput, but how is NVIDIA planning to optimize memory efficiency at the intersection of quantum classical workflows, especially for models that use emotional feedback loops, trace-based memory pruning, or time-based semantic recall, like my own child AI.py system? Traditional memory hierarchies choke on nonlinear growth. Does your team envision a framework for dynamically self-refining memory states across quantum classical?
Yeah, I'm not familiar with the child AI.py system.
Is there the memory model for quantum computing? Is that something you could discuss?
I'm pretty sure what they mean here. It's hard to answer, sorry.
That's quite all right. I'm just going to keep moving on.
It's a general comment on, what do you think about CPU and GPU systems, or CPU, GPU, and QPU systems? One of the biggest challenges in these systems is moving data from one system to the other, right? So we know that it tends to be a bottleneck between CPUs and GPUs. NVIDIA's architectures that remove that bottleneck or open that bottleneck up are the Grace Hopper and Grace Blackwell systems that have a high bandwidth and coherent memory across CPU and GPU. And part of the design inspiration behind DGX Quantum is to extend that to QPUs, right? So that's where that low latency quantum machines interconnect comes in. So it's designed to have low latency communication between CPU, GPU, and QPU, and then memory movement is still up to the user or the designer of that algorithm.
Okay. Is there any use case of quantum computing in digital security, cryptography, optical fiber for BIF sector?
Yeah, so one of the long-term use cases of quantums actually can be leveraged to break certain types of encryption. So this is something that has a long-term kind of application leveraging Shor's algorithm. The good news is that there's also quantum-safe encryption algorithms that actually the US government and NIST is recommending. So there's a number of different quantum secure algorithms that can also help protect from a future quantum attack.
Okay, we'll move on to this one. How many qubits on average are needed to are being used for computation? How many do you believe are needed for practical applications to be useful?
So I think today we're using probably on order tens to maybe a few hundred physical qubits. And I want to make the distinction between physical qubits and logical qubits. So physical qubits are necessary to build up so-called logical qubits. So once you have a number of high fidelity physical qubits, you can start building up smaller numbers of logical qubits. And the logical qubits can maintain their information for much longer periods of time and have much, much lower error rates. And this is kind of what we hope to achieve with quantum error correction. So in terms of physical qubits, we're currently at the stage where there's maybe tens or hundreds of qubits, physical qubits used for noisy intermediate scale computations. In terms of logical qubits, people have shown, of order a handful of logical qubits made from many physical qubits. So in terms of what's generally agreed upon for achieving some sort of useful application, we'll probably need on order of say 100 logical qubits, which would correspond to something like 1 million physical qubits.
Okay, we'll move on to, are there pre-built QML examples using the parameterized circuits? How exactly does CUDA GPU specifically benefit quantum applications and programs? Do quantum programs also take benefit of the parallel processing power of GPUs? Got cut off there on the end, but basically the interplay with the GPU.
I can take that. There are definitely one of the specialities of my team, which is the quantum algorithm team. We work on a lot of applications that use machine learning in general. So there are a lot of applications using machine learning and parameterized circuits that are available in our repository. One simple example of parameterized circuits is what is often used in variational quantum eigensolver, or VQE. So there are certainly examples available with that. There are also examples of quantum neural network, which might be close to what you are asking for. So those are definitely available in the CUDA quantum repo. How exactly does using CUDA quantum benefit quantum application programs, right? So CUDA quantum provides this sort of like seamless integration between GPU and QPU compute. So that's one obvious way where the applications can benefit, right? Another one is if you don't have a QPU available to you, or if you want to experiment with applications where QPU compute is currently not possible. So we do have amazing GPU simulators, which can really help with productivity when you're trying to develop these applications and algorithms. So for example, in context of VQE or this quantum neural network example that I gave, oftentimes you have a bunch of parameters that you need to feed into your circuit. And you need to run a whole bunch of circuits with a whole bunch of parameters. And that's a very compute heavy problem. What CUDA Quantum can do, it can provide something called batching of the circuits or batching of parameters. So you can actually run all of these circuits in parallel using these different parameters and collate the results. So we have, if you want to sample the results, we have something called sample_async. And if you want to find the expectation value, we have something called observe_async, which is meant, and the main use of that is to be able to leverage a whole lot of GPUs to run all of these circuits in parallel and asynchronously, and then collate and post-process the results as you please. So yeah, GPU compute is very, very useful. And apart from like using as a simulator, oftentimes we need to pre-process the data or post-process the data. And that's where also you can parallelize things using GPU and really accelerate your applications.
How can I apply these concepts of CUDA-Q and quantum computing to drug discovery, specifically molecular dynamics simulation? And what advantages could offer if it is feasible for this application?
I can take this one. Yes, there's a few ways that quantum computing could address different use cases in drug discovery. Thinking about our applications page, you can actually go look at some examples. We have two that I can think of off the top of my head. One is an optimization problem where drug docking is set up as a QAOA problem, and you can see how you could map that sort of problem to something that could be solved on a quantum computer and potentially help when you're trying to look at the behavior of drugs mapping to some large protein. Another example that's more specific to the question you asked about molecular dynamics, we have an example of something called a QM-MM simulation. And this is where you have a quantum mechanics part of some set of molecules and then a broader molecular mechanics part. And then the quantum computer could be used to solve and predict the energy of that QM part kind of in the region of this molecular dynamics simulation. So you could get a much more potentially a higher accuracy result in that region by whatever method you apply there. And then what's cool about that is any quantum computing or classical quantum mechanical method could be used to perform that sort of simulation in that QM region. So it's a way to pair classical methods with quantum computing. And then as quantum computers scale up, they should be good at simulating chemical systems and potentially allow us to make better predictions beyond what we can do today.
Okay, let's move on to, can we use it in AI agents?
Yeah, you should be able to. We know that people are using that in order to learn CUDA-Q and to write CUDA-Q code or improve CUDA-Q code. We make sure that our documentation and all of our resources are AI agent friendly. So you should be able to use that as a source of information and help you to write code or learn CUDA-Q or get better at CUDA-Q. We're happy to hear also from everyone's experience on how they're working with the AI agent and how does it work for them for CUDA-Q, if there's anything else we need to improve. We know that most developers right now are using AI agents and Copilot and other tools to write code, and yeah, we think that's great. Makes it much easier for people to use CUDA-Q.
Awesome. So I'm going to move on to this question. When do you estimate we will reach a real-world Q-day scenario where brute force quantum hacking becomes viable via Shor's algorithm?
That's really difficult to answer. And the nice thing about kind of our strategy is that we are developing quantum safe algorithms for everyone to accelerate their adoption of quantum safe algorithms, but it's really difficult to predict when any sort of kind of application will come online on quantum computing.
Yeah, and I think we talked through some of the various scale factors needed to reach, fault tolerance at scale, right? So Jin kind of laid out these factors of 1,000 to have 1,000,000 physical qubits for 1,000 logical qubits. And you can think of all of the intermediate steps there, especially for doing quantum error correction at scale, being able to do that in a time that, is relevant to that underlying physical platform. So I think there are a number of challenges to be solved in that area, and CUDA-Q is providing the platform for researchers to build those solutions.
Let's see, what strategies is NVIDIA employing to optimize qubit stability and efficiency, particularly around intelligent memory handling?
So I'm not sure about the intelligent memory handling part, but in general, CUDA-Q is also used by QPU builders to optimize and build the qubits and gates. The way that they do it is they use the dynamics backend of CUDA-Q. This backend really allows to simulate open systems and hardware systems in efficient ways. So they can first simulate that on GPUs. And that's a way for them to optimize their hardware. And maybe Jensen can tell a bit more about specific companies that have used it, the dynamics.
Yeah, so we had a really nice demonstration with the Google Quantum AI team last year. So really the benefit of being able to simulate the actual physical processes of your qubits is you get a deeper understanding of kind of the different ways they interact, quantum objects interact with each other in a given system and how they also interact with the environment. So this is really critical to understanding where the losses in fidelity are coming from in your qubits and where the losses to the environment or other kind of higher levels of the quantum systems where information might be leaking to. So that gives researchers a really fine-grained tool for examining the interactions in a quantum system.
Okay, great. I'm going to go ahead. This is going to be our last question. I'm so sorry we're not going to get to everybody's questions, but this is, I think we're going to have to wrap up on this one. So what is the best way to bridge CUDA-Q in Python and, I'm sorry, Julia for hybrid quantum algorithms? So the reason I pulled this one out is really talking about the interplay between Python and Julia and quantum algorithms. You guys want to comment on that one?
Yeah, so various folks have actually built cuQuantum backends for various Julia packages. So I would say the best way to bridge it is to submit a pull request, build it. It's open source, leverage the tools that we've put out into the ecosystem, and then put in a pull request.
All right, easy enough. Well, with that, I really want to thank our wonderful panel here for answering all of these questions and bringing CUDA-Q out here in the Connect with Experts webinar. Just to let everyone know that this will be available on demand through our On24 on-demand system after this event is over. So please feel free to check it out, share it with your friends. And please join us next month on August 30th. We will do a webinar with our Python packaging team. So we have a panel of people who talk about the interplay between open source and CUDA teams in order to be able to package accelerated Python applications. And I hope to see you there. Thank you so much for your attention.